All right, in this problem, we're being asked to maximize the cross-sectional area of this gutter that's created from taking a 20-inch wide flat piece of sheet metal and bending it on the sides in equal lengths to create the figure that we have right here. The idea is, so we take this 20-inch wide piece of metal and we're going to make a bend the equal distance on both sides here. And it's important that they have the equal distance because we want the sides of our gutters to be the same. So those sides that I'm painting over there are the same as these sides. So what we're going to do is going to call the height of this gutter X. And so this length right here, that the length of this bend is going to be X. The key is, the question becomes, what is this length right here? What is the width of this gutter if I bend it at X? Well, it's going to be the 20 inches minus whatever the length of this height is times 2, because I'm going to do it to each side of this. And so the width of this gutter would become 20 minus 2x. Now, the question that's being asked is to maximize the cross-sectional area. The cross-sectional area is the area of if we transposed a rectangle here onto this gutter all the way across, it'd be maximizing the area here of this gutter. And so what we do is we're going to create a function for this area. In this case, we would just do length times width, and so the area being length times width, we just need descriptions for the length and the width, and so the length here would be this 20 minus 2x, and the width, or the height in this case, would be this x right here. And if we're being asked to maximize the area, what we just need to do is we're going to FOIL this out or distribute this. Think of this as a quadratic and find the vertex, which would be the maximum point. So real quick, this would become 20x minus 2x squared. And written here in standard form, we'd have this lead term first, negative 2x squared plus 20x. Okay, and in this case, this x represents this height of the gutter. And then this expression right here, given that x represents the height, represents the area or the cross-sectional area of the gutter. If we're being asked to find the maximum area, we now have this function or this expression that represents it. I think a very useful way visually would be to graph this function. And so here is the graph of negative 2x squared plus 20x. Again, along the x-axis, this is the height of the gutter, or the cut of that x. So this point right here represents that if you make that height 2, the cross-sectional area would be 32 square inches. Obviously, as we go through here, so again, this y-axis or the f of x axis, it represents that cross-sectional area. Again, because our expression over here is derived in such a manner. Well, this point right here at 550 is the vertex, giving us that if we make that x cut, or that cut, we bend those sides at 5 inches each, we'll get our maximum area of 50 square inches. So that's just looking at it graphically. If we wanted to, we could compute that also using the vertex formula. So we find the vertex with x equals negative b over 2a. And in this case, that would be negative b would be negative 20 over 2 times a, which is 2 times negative 2. Simplifying that real fast. So this is telling us that it occurs at 5, or when x is 5, and again, x represents the height of the gutter, or that the length of that cut right here, which is the same. And then if we wanted to find out what that area would be, we would simply just plug 5 in to our expression. And simplify. And so again, in finding that out, that agrees with our visual description here of this graph, that the peak point, that vertex point, which is a maximum, and just to speak of, it's a maximum because this lead coefficient is negative, making it a concave down parabola, is the maximum area, and that occurs when the cut is, or the bend is at 5, and it gives us a maximum area of 50 square inches.